Okay, we're back, and I wanted to really go into a little about the constant. Suppose we have three cost functions, and here's a cost function with the variable cost is x squared, but the cost function, the fixed cost might be 5. Now it could be $5,000. This cost function for another, let's say another part of the industry, is also x squared, but the fixed cost is now 100, maybe 100,000. And this cost function is also x squared in terms of variable cost, but now the constant is 1100. Well, if we take 0, 0, 0, that's like 1.1 million. So those are three different fixed costs, which obviously, if you didn't know those numbers, they add significantly to the cost. But now if I take the first derivative of each of these, notice I get the same thing. X squared, x squared, x squared, because the derivative of the constant is 0. Thus, if we did not include a constant in our integration, we cannot recover our complete original functions from the derivatives. Well, that would be dreadful for companies like this. I wouldn't know whether my fixed cost is 1.1 million or 5,000. So that's why we have to recover the constants. Now, why do we only have one constant? Okay, so why only one constant in every integration? Well, let's take another example here. And I think I developed it. I'm not sure if I have it right now. But let's return to the comparison page. And you know what? Before I go into this, let's do some integration. Because this is basically, I could have, well, let's say I have the total cost. I have an industry which has two companies with it. I have the first company plus the second company. I'm going to have here, let's say this is x squared plus 10, and this is x cubed plus 100. Well, when I solve this, I would x squared plus x cubed, and I would add these. So that's why, even if I'm talking about two different suppliers to an industry or something like that, I always add them. So I put everything in one constant term. So that's an easy way of describing it. I did have a graphical method, but this is an easy way of doing it. If I had CT, so my CT would have a total fixed cost of 110 for the company, which is fine, and that's what I'm finding. I'm finding the total function for this particular company for their operations. So we always would add up the constants anyway. So that's why we lapse all the constants, all our fixed costs, for example, for our company into one term. So let's go and let's do some more integration. And then we'll go into some practical examples. Let's leave the formula on the board. So as we can see, the constant is very important. So let's take, let's say y equals 2x to the minus 1/2. And that would be y prime. So I'm given that. So that's your derivative. I want to find yx. I'm going to rewrite this, dy dx. I'm going to multiply both sides by the dx. I'm going to put the integral sign there. Now I'm ready to use my rule.
dx.
Oh, I've got a dx, sorry. Dx is called the differential. It's a small piece of the curve. Here a is 2, n equals minus 1/2. So y is going to be equal to 2x minus 1/2. Don't forget this is plus 1. Remember, with the derivatives we were subtracting. Since we're going backwards, we're adding. One of the biggest problems when people go from one to the other, plus the constant. All right, so this is going to be equal to 2x minus 1/2 plus 1 is going to be 1/2 divided by 1/2 plus c. Now everybody should know that when I have to do this, if I want to bring this up, I have to flip it. So y is going to be equal to 4x to the 1/2 plus c. And that's my answer right now. If this was a practical problem, I would have to actually solve for c. Let's do another one. Let's get our feet wet on integration. I can put another one over here. This is easy. Okay, so I'm given, this is example 2, I'm given y prime equals 2 times the third root of x. I want to find y of x, the function. So let me rewrite this one as dy dx equals 2, and I'm going to write this as a power. I mean, that's a 1 here. Remember, you can write this as x, this over that. Multiplying by dx, both sides, and putting the s sign on, the integral sign on. So now we're ready to use the power rule. A equals 2 and n equals 1/3. Well, that becomes y equals 2 x 1/3 plus 1, 1/3 plus 1 plus c, the constant. So y of x is going to equal what? 2. Well, what's 1/3 plus 3/3? So I can write 1 as 3/3. It's x to the 4/3 over 4/3 plus c. What do I do with the 4/3? Well, I write t. I write the 2 and I flip the denominator. So y of x equals 6 over 4, x to the 4/3 plus c. If I wanted to simplify that, I could make this 3/2, but I'm just going to leave it that way right now. I'm really interested in learning how to integrate, not reducing fractions. So let's try now one with multiple variables. So let's take another example. Example 3. And here I have the y prime, or we can make this f prime of x if we want, equals 3 times x third plus 4x. Well, what I might want to do is expand this first. So I get 3x third, distribute the 3. Now I can rewrite this as what the derivative really is. multiply both sides by dx. Put your integral sign on. Now your integral sign has to be put on both parts.
dx.
And there's, I forgot the dx, thank you. 3x third plus 12x times dx. We won't put the integral sign on yet. So now we want to distribute the dx. 3x third dx plus 12x dx. And now we'll put the integral sign on. Got to do it on each term. A term is something separated by a plus or a minus sign. So we can do each one separately if you want. Here a equals 3 and n equals 3. Here a equals 12 and n equals 1. So this will become f, and this will become 3 x3 plus 1 over 3 plus 1 plus 12 x1 plus 1 over 1 plus 1 plus c. What we get here is, this becomes 4, so it's 3 over 4 x to the 4th plus 12 over 2 x squared plus c. So finally the function is 3/4 x 4th plus 6 x squared plus c. So remember the original function was 3x third. Now if you want to check your work, just take the derivative. This will be 4 times 1/4. This will be 3x third plus 12x, and the c is gone. 3x third plus 12x. So now you've checked your integral is correct, because when you take its derivative, you get back the original derivative which was given to you. All right, so we want to do some more. Now, be very careful. No matter how many terms we have, remember when I did the cost thing where CT was C1 plus C2? No matter how many terms we have, we're only going to have one constant. Remember? Theoretically here I have two constants, but I'm going to add them up and lop them into one constant. So if I had 3 terms, I'd have 3 constants, but I'd add them up and lop them into one constant. That's the concept. All right. So let's do some more polynomial integration. And let's get this off here.
We got 1 minute.
All right, so we have 1 minute till the end of this class, right?
Yes.
So I'm going to be working on this problem. Okay, example 4. F prime of x equals 5x to the 4th minus 9x squared plus 3. And I want to find f of x. And I want you to do this before the next class. And I will go over it using the rules that I did today. See if you understand what I did today. I will see you on our next lecture.